So, welcome to the course Digital Human Modeling and Simulation for Virtual Ergonomic Evaluation. Now, we are going to discuss this module for week 4, Introduction to Digital Human Modeling and Simulation. So, in the last 3 modules, 1, 2 and 3, we discussed various aspects of design, ergonomics, virtual ergonomics. Now particularly we will discuss about digital human modeling and simulation in module 4. In module 3 we mentioned what is digital human model. Just for recapitulation, we are again discussing that what is digital human model. CE in 2003 defined digital human model as this is computer graphics mannequin or digital human model. It can be defined as a 2-dimensional or 3-dimensional graphical computer representation of human body based on anthropometric measurements, link and joint structure and movement characteristics. In other words, we can define what is digital human model. Digital human models are 2-dimensional or 3-dimensional representation of human body based on anthropometric and biomechanical data, and those models are used for virtual ergonomic evaluation of product and workstations. These digital human models are of 2 types. First one is physical and second one is cognitive. So here is one example. These digital human models, male models and female models, created using JAX software, where we can see that different population databases are already incorporated in that software, and based on those databases we can create digital human model. So digital human model is of 2 types. One is physical human model, another is cognitive digital human model. Now what is physical digital human model? Physical digital human modeling is concerned with physiology, anatomy and various occupational ergonomics aspects. Physical digital human models, again we can categorize in 2 categories. One, biomechanical model, and another is 2-dimensional or 3-dimensional structural model. This biomechanical model, we discuss about various softwares are there. For example, 3ds SPP, ErgoWatch, NIOS and Snoop tools. So all these are coming under biomechanical model. And under 2-dimensional or 3-dimensional structural model, we discuss about various 2-dimensional or 3-dimensional representation of human model, human body form. An example of such softwares are JAX, SAMI, Ramsey, SafeWord, Delmia and so many others. So overall, this physical digital human model mainly concerned about biomechanical aspect, anthropometric aspect, and while we are evaluating any workstation, we are checking the human compatibility with the machine, we use this type of physical digital human model. But the digital human model which we are discussing in the present course, that is mainly related to 2-dimensional or 3-dimensional structural model. Next, another type of digital human model is cognitive digital human model. It is still in development phase because in many universities and research organizations in this particular area research is going on and new research findings are coming out. So this cognitive and or performance digital human model, what does it deal with? Cognitive and performance digital human modeling and simulation of human beings include modeling and simulation of human behavioral aspects, artificial intelligence, interactivity of synthetic agents, etc. So these are the areas which cognitive digital human models deals with. Example of such softwares are CASE or Computer Aided System Human Engineering Performance Visualization System PVS, then NASA TLX and so many others. But these softwares as well as overall the cognitive or performance digital human models, these are still in primitive stage and enough research is required for developing this particular field. Now, evolution of digital human model. When this digital human model started and gradually years after years how it evolved. So, if we look, initially digital human models were developed as stick figures. More complex representation of body segments and joints with finer details gradually came. Next, physical digital human models usually constructed on the basis of rigid framework or link segment. Framework usually covered with solid geometric shapes to give visualization of human body surface. So, initial it is rigid framework of link segment, then gradually it is solid geometric shapes. So, these solid geometric shapes, earlier those models are robot-like because in the software geometric primitives like cylinder, then different types of polygons, then sphere, all those basic forms are used. Gradually, with the advancement of computer technology, complex geometric models and smoothing algorithm came. Then it is possible to develop body shapes or morphology with surface modeling. Later on, the surface geometry were further developed, which represented human skin, then various types of clothing, protective equipments. Those types of development happened in this field. And more recently, in this software, CentOS, it is developed by Virtual Soldier Research by Iowa University. In that software, we can find very realistic skin deformation, contracting muscle in very advanced digital human model gradually came in the market, which initially started with stick figures. Now, advanced digital human model softwares are available where we can go for various types of virtual ergonomic evaluation, and those models are very realistic in terms of anthropometry, in terms of body motion, in terms of various analysis, and also as for look also. So, if the whole whatever we discussed in earlier slide, the whole information, if we summarize, it moves like this milestones. So, initially it was stick figure, then geometric primitives are used. Gradually, complex geometric modeling with smoothing algorithm came. Surface modeling for appearance of skin and clothing, it was started. Then incorporation of 3D body scanner data directly. Earlier for digital human model, physical anthropometric measurement and those data are used for this purpose, but nowadays directly we can import the data from 3D body scanner, and those data is used for developing digital human model. So, those digital human models are much more realistic. Not only 3D body scanner, then 3D motion captured data, human motion in 3D space, that has also been captured with camera, and those information is incorporated in for posture prediction, various types of activities. So, that is also included in this digital human model software. So, technology like 3D body scanning, 3D motion analysis, all those are now being incorporated in advanced digital human modeling software. Then incorporation of predicting dynamic human motion for realistic posture and task simulation, that is also done. Realistic high fidelity digital human models with finer details, as for example skin deformation, muscle contraction, that is also going on by various software developers. The whole evolution can be represented like this type of diagram. So it started from stick figure, then geometric primitive, then it moves towards wireframe, then various type of shaded representation only for the skin and body shape, for showing the body shape. But not only that body shape, or after that gradually it moves towards this type of skeletal figure, not only skeleton, on that muscles also. So for example, in anybody software there is muscle also. After that, more realistic representation like skin deformation, clothing pattern. So all these things gradually being incorporated in various digital modeling software. So among the advanced software, one is CentOS, where we can find all these realistic skin deformation, then muscle movement and all. Now next we are moving towards the history of various digital human modeling software which developed years after years, started in the long back like 1960s by Boeing Corporation USA. They developed the first digital human model which is known as Boeman. So we are starting from that software Boeman. So if you look at those models, you will understand those models are very primitive in nature. The first virtual mannequin named First Man, later on it was named as Boeman, was developed by Boeing Corporation USA in 1959 to assess pilot accommodation in the cockpit of a Boeing 747 aircraft. The First Man was composed of 7 movable segments which could be articulated at pelvis, neck, shoulder, elbow in manners resembling to human motion. The First Man evolved up to 4th generation, that is 4th man and woman version, as it is found from the information provided by Morrell 1998. The First Man was also the first virtual human used as animated human for commercial purpose. So this is one image from that software. Next, after Boeman, now there are so many other software, Cyberman, SAMI. So one of the first the DHM software was Cybernetic Man Model Cyberman. Cyberman was developed in 1970s by Chrysler Corporation for their in-house design and evaluation of automobile. Then other software like SAMI came. SAMI, full form System for Aiding Man-Machine Interaction Evaluation, is a computer-aided human modeling, ergonomic design and evaluation of system. Developed by Design Ergonomics Group in collaboration with Wolfson School of Mechanical and Manufacturing Engineering in 1972. This is one of the first kind computer-based digital human modeling program for ergonomic evaluation. It consisted of well-developed vision system and manipulation of complex objects. So after Boeman, Cyberman, SAMI, so many other softwares also came in the market. One software is CombiMan, computerized biomechanical man model known as CombiMan. Later on it was known as CrewChief. Was developed by University of Dayton, and further development took place in US Air Force Medical Research Laboratory AMRL during early 1980s for simulating pilot and aircraft maintenance tasks. So in 1980s CombiMan software came. CombiMan as both illustrative and analytic software which is capable of analyzing physical accessibility, reach and fit capabilities, strength for operating control and visibility, accessibility, etc. Then gradually more advanced software came. In mid 1980s, N. Butler and his research team developed the software Jack. This is a computer graphics software where now it is being marketed by Siemens PLM Solution. The Jack software, initially it was known as Tempus, and it was developed by Human Modeling and Simulation Group, University of Pennsylvania, and it was funded by NASA and US Army. And if you look at the models, so this model relatively more realistic than the earlier models. In this 1980s, 1990s, during this period, other software also appeared in the market. One of such software is Ramsys. The realistic anthropological mathematical system for interior comfort simulation, known as Ramsys model, and it was developed in 1980s. It was developed as a cooperative arrangement between German automobile manufacturer and Technical University of Munich, Germany. So, by collaboration of this TechMath and University of Munich, this software came. Ramsys is used extensively in automotive industry, from various types of passengers, starting from passengers car to heavy vehicle, as well as even for aerospace industry. This software is being widely used nowadays. Another software, SafeWork. SafeWork software was developed by SafeWork Inc., business unit of Dassault System. It can determine various variables such as lifting, lowering, pushing, pulling, weight limits suggested by Nernst lifting equation. Some other software, as it is mentioned here, Mannequin Pro. Mannequin Pro is a PC-based human modeling software. It is available since 1990. Mannequin Pro was used by Air Operations Division in late 90s to assist in the evaluation of pilot in a Black Hawk helicopter. So, how these models can be used for helicopter cockpit simulation, it has been shown by authors, as in case of, you can go through this reference, then we get more information. Another software known as LifeMod. It came to existence around 1990s with constant development over 2 decades. It can be integrated with other software like MD, Adams. LifeMod has powerful post-processing capabilities to produce standard plots of force, displacement, velocities, accelerations, torques and angles. Using a 3D motion capture system, we can also incorporate human 3D motion data to this software, and we can create lifelike the motion of digital human models. So, down the line, another software, this Anybody, it came into existence and became popular during 2000. The Anybody Research Group was formed in 1997 at Aalborg University in Denmark and globalized around 2002. It helped to build more complex whole body model and developed ergonomic optimization in design. 3D biomechanical model that was based on the theory of mechanical structure of the musculoskeletal system shows a mathematical resemblance to a solid articulated structure in which the load carrying elements, bones, muscles and ligaments are used to their full potential to stabilize the configuration of the structure. So in earlier models, what we find, that is mainly either link segment and skeletal structure is covered with surface modeling to represent the human skin or shaded model. But in this model, what we can find, with the anatomical bony structure is covered, skeletal structure is covered with various muscles. Even with this software, we can create models, antibody models that may be composed more than 500 individual muscles. So while we are discussing or while we are going for analyzing various types of biomechanical analysis, then this software is very much helpful, because there we can analyze the full potential to, then we can analyze the motion of bones, then muscle contraction, activity of ligaments. So all these things can be analyzed using this type of software. Most advanced among this available software, what we find, that is in terms of features, the software is called CentOS. The CentOS was developed by University of Iowa and in 1998, and it was funded by Virtual Soldier Research by US Army and University of Iowa. Under the project Virtual Soldier Research Group, they developed this software. This software right now, among those available softwares, it is considered as one of the best software, because in this software we can find the skeletal structure covered with surface model, and it includes realistic skin deformation, contracting muscle. All these things we can go for physiological evaluation, biomechanical evaluation, effect of various environmental variables. Those can also be studied with this software. So this is really an advanced software. The software package, the CentOS software package includes biomechanical models and simulation of human motion, posture prediction, strength, fatigue, and also physiology. So this information, you can get more information from this reference, Ritchie 2011. Now, so what we discussed so far, we discussed about how digital human modeling software evolved starting from 1960s still today, and various digital human model softwares which came in the market in different time period. Now we are moving to interfacing CAD product or facility with digital human model. How we can do that one? So this schematic diagram proposed by Patel et al. 2016. So what they proposed, what input is required? CAD. From CAD software, where we can consider various design variables for machine tools or any other equipment or device design, and considering all those variables, we can create the CAD model of the product or any other facility. So in this side, using CAD software, we are developing CAD model. On the other hand, we are developing digital human model. Using digital human modeling software, various human factors variable related to anthropometry, related to biomechanics, we can consider and we can create human model. When this product CAD model or facility CAD model is ready and human CAD model is also ready, then we can go for interfacing those. Interaction between human and product. After that, we go for various output, simulation parameters and simulation analysis. So after analyzing, we can go. So this step is for virtual ergonomic evaluation of that product or workstation or any other facility which we are developing. So details information regarding this reference you will get at the end slide. Now if we represent the same thing in schematic diagram, so what we do with digital human modeling software, where you can use anthropometric data as well as biomechanical data. For initially it is used anthropometric data, we can create this type of digital human model. Even we can change the various biomechanical variables also, like range of motion, comfort range, also those data we can fit in these types of digital human model. And when the digital human model, we can, earlier also we discussed, we can create customized human model. Customized human model means we can create as per age variation, sex variation, anthropometric variation as per various percentile data. So here it is shown that 5th percentile Gorkha soldier from India, then 50th percentile pool data of army, and 95th percentile Sikh Punjabi soldiers from Indian army. So these are the representative of smaller Indian army personnel, average Indian army personnel, and larger Indian army personnel. While these models are ready, then what we are doing, we can generate solid model of this type of product or facility. Here it is a army vehicle. In army vehicle, this type of army vehicle we can create, or any other product or facility we can develop using either with the help of this type of digital human modeling software, but many digital human modeling software does not have such capabilities to develop very complex CAD model of the product or facility. For that purpose, what we do, we develop this type of product model from other CAD software like SolidWorks, CATIA, Unigraphics. So this type of various ideas, so various softwares are CAD softwares are available. With those CAD softwares, we can create this type of product or facility model, and we can import those model in digital human modeling software. Then what we do, we go for interfacing this digital human model with the product or facility or vehicle model or workstation model. For that purpose, what is required? We have to give appropriate working posture in that workstation, in that facility. What's the activities, required activities those human models is required to do, that type of posture we have to give, and we have to position those human models inside that workstation or that facility. While human models are properly positioned, then we can go for various types of virtual ergonomic evaluation. We will discuss what type of ergonomic evaluation we can do with this type of software, with this type of digital human modeling and CAD software. So if we repeat, so first we are creating digital human model of various percentile, or even we can create as per individual data. At the same time, we are either creating this type of product model using digital human modeling software, or we are importing this type of CAD model of the product made from other software like say Unigraphics, CATIA, SolidWorks. After that, we are importing that model to that digital human modeling software interface, and we are putting those human models with appropriate working posture. Then we are moving towards ergonomic evaluation. Now here we will discuss one example. In this example, for tractor cab design, so this is taken from Patel et al. 2016 schematic representation of ergonomic evaluation of a 3D tractor cab model with digital human model. So how we do that? If we want to evaluate a CAD model of a tractor in virtual environment, how should we proceed? First, database required farmers or tractor operators related database. So anthropometric that is static and dynamic dimension is required. Then biomechanical information, biomechanical data related to range of motion, force, torque, etc. required. Then comfort range, single joint, multiple joint comfort data is required. So these three areas, anthropometric data, biomechanical data and comfort range data. While these data are ready, with those help of those data, we can create digital human model. Digital human model of tractor operator or farmer who will operate the tractor. While that human model is ready, then what we are doing? Human motion simulation, that information creating virtual 3D human. That information also we can put, and we are creating 3D virtual environment. So from this side, based on this database, we are developing digital human model of tractor operator or farmer model. On the other hand, we require cab information, the tractor cab. For that purpose, we go for need identification, design limit selection, various design. Those design limit selection mean various dimensions, material selection, cost, all this. Based on that 2D sketches and concept development. While the concept development is ready, then we are using various types of CAD software. With those CAD software, we are developing the 3D CAD model of that tractor cab, and also we are rendering that one. So digital cab model of the tractor, design variables like driver seat, steering wheel, various types of foot controls, hand controls, display dashboard, all those are made. So from this side, digital human model is ready, and from this side, tractor cab model, 3D CAD rendered CAD model is ready. Then we are interfacing. Digital human models are given actual working posture and CAD model, and it is that models are positioned in tractor cab model. So we are getting that virtual environment. In this virtual environment, both digital human models are present and tractor cab model is also present. While that virtual environment incorporating CAD model of the product and human is ready, then we are moving towards ergonomic analysis. What ergonomic analysis we can do? We can go for various types of ergonomic evaluation for this tractor cab. For example, we can go for vision analysis, interior and exterior visual fields from driver seat, reach analysis, reach towards various types of foot controls, hand controls. Then working posture, driving posture, driving comfort, clearance interference, ingress egress, whether the driver can easily enter or come out from the driver cabin, and various other analysis we can do. At this phase, if we find after evaluation with digital human model, if we find that whatever concept model we develop, if that is fine as per the ergonomic evaluation, then we will proceed for final design concept and prototype making. If we find no, there is some modification or redesign is required, then again we will go for redesign and modification phase, and again we will modify the tractor cab model, and again we will go for further ergonomic evaluation. While ergonomic evaluation is satisfactory, if we find that tractor cab model has been designed as per various human factor issues, it has properly incorporated or it has been developed as per various human factor issues, then we will go for prototype making, and finally is documentation. Now, what are the functionality of digital human model? So basic functionality of any of these digital human modeling software, whatever softwares we discussed, that may be Jack, that may be Sami, Ramsys or Santos, for all these softwares, basic functionality is creating digital human model. Well, regarding this digital human model creation, we, as we mentioned, we can create customized human. Human model as per our intended user population or intended user, and any sort of variation in terms of anthropometry, somatotype, we can do that. Then we move towards building virtual environment. Virtual environment, making the CAD model of the product or importing the CAD model of the product or workstation from other CAD software. Other CAD software developed workstation model, and interfacing these two, human model and virtual environment or virtual product model, then we interfacing with appropriate posture. So these three are the basic for any software. Then software to software other functionalities varies, but few basic functionalities are there in almost all these softwares. Those include reach analysis, vision analysis, clearance interference study, comfort discomfort analysis, fatigue analysis, various types of postural analysis using various types of postural tools like ruler, REBA, WAS, NIOS, etc. Then posture prediction based on preset criteria, lower back analysis, spinal compression forces, shearing forces we can analyze. Not only that, even metabolic energy expenditure, predetermined time standard, static strength prediction, various type of packaging guidelines as per Society of Automotive Engineers or any other standard organization, as per their requirement we can also analyze our product or workstation. So these are the some basic functionalities which is available almost in all the developed software which are right now in the market. Now Stephen and Jones 2009, Bob and Fritzke 2009, they mentioned digital human modeling or digital human models or digital human model software has the capability to interact with digital workstation, and subsequent various types of ergonomic evaluation is possible. As ergonomic evaluation, they mention we can study workstation layout, workflow simulation, assembly accessibility, reach analysis, clearance analysis, strength capability studies, safety analysis, assembly feasibility, others like process compatibility issues, posture and movement simulation for various body parts movement, then inverse kinematic, forward kinematic, different types of kinematics for posture, giving the appropriate working posture or simulating various types of tasks, then vision simulation, then comfort analysis based on single body joint or multiple body joint, then maximum force calculation and center of gravity analysis, biomechanical information, spinal compression. So they mention all these types of analysis actually we can perform with the help of digital human modeling software, and that's why digital human modeling softwares are very much essential for proactive ergonomic evaluation of various types of product and facility in production engineering or manufacturing sector or in production plants. Now we want to discuss how these digital human models are created using digital human modeling software. So software to software it varies. From one software to another software, interface is different. You will find in some software we can create that user interface is very user friendly. In some software it is little bit difficult, you have to learn. So here we are giving example from CATIA software. In CATIA software we can create digital human model. For that purpose, if we open that software, we will find the start menu. Under start menu there is one sub menu called ergonomic design and analysis. Under this ergonomic design and analysis we will find human builder. There are four options: human measurement editor, human activity analysis, human builder and human posture analysis. While you are creating digital human model, we want to create new model, then we will follow this step. From start we will go to human builder. While we will click on human builder, it will open this particular window where so many other tools are there. So first we will use this tool. This tool is insert new mannequin. For inserting new mannequin, while we will click on that one, it will open this type of window. In that window, which informations you need to put, first one is you have to select a product. First, there should be a product tree. In that, you have to identify that human model which you are going to create that is associated with this product one. Now, mannequin name. You can put the name of the mannequin, mannequin 1, mannequin 2, or any other particular name, the 50th percentile model or 5th percentile model, or whatever you wish. Accordingly, you can put the name. Then you can specify the gender, whether that is a male model or female model. Then you can go for percentile, which percentile model you want to create. You can create as per your requirement various percentile, starting from 1st percentile to 99th percentile or 100th percentile. After that, while you are clicking on OK, then this type of models are created. Human model is generated. Now, while this human model is generated, now you can go for further modifying individual body parts based on anthropometric data. For that purpose, you have to follow this path from start, then ergonomic design analysis, under that human measurement editor. Then under human measurement editor, when you will click on human measurement editor, this window will open. In that window, you are first selecting this one called filter. In that filter, various parts are there that you can go for part, body, head, torso, arm, hand. In this various body parts are there. Types, what type of anthropometric variables you want to consider, like circumference, height, length, breadth, depth, mass. So all this is possible. Now here we can go for manual. If you want to manipulate it, you can put it manual. Then we can go either one or individually, or we can select all at a time. So while you are putting all, then all the body parts and its all types of anthropometric variables will be displayed on human body, and each of the body segment and its anthropometric dimension we can modify. So here it is shown that how we can to change the dimension of any body part. Double click on that part. If we double click on that one, then this type of window will open. If we say, for example, here okay, so from front to back, if we say this is the head depth, or to back of the protection to back of head, it's not clearly visible anyway. So if we want to decide the head dimension, then we can select this particular dimension. While we will click from that list, that will be highlighted, and when that is highlighted, then you will find that variables, various values are shown there. Now as we are manually manipulate that dimension, for that purpose we are selecting as manual. Now if you want to create which percentile, you can put it here. Otherwise, if you have anthropometric data for that particular percentile or for individual, then you can put that value here. While you will put that value here, automatically it will change the percentile value as per the incorporated database. If the database is not there incorporated for a particular population, then as per the particular population anthropometric data, we can put the dimensional data for specific body parts. Then obviously gender, here it is man, and construction, this is standing. This is for these dimensions are for standing posture. Similarly, we can find for sitting posture also so many other variables. So here you can find 103 anthropometric variables are there for constructing this digital human model in case of this CATIA digital human model, which is also known as Delmia human. So this is one example from CATIA software. From other software, say now if we go for other software, if we see the interface of JAX software, in JAX software we will find this type of interface where we can put the dimensions. So first we are creating new human model. In that new human model we can create that which human model we want to modify the body dimension. We can put the name of that. We can specify whether we are creating male model or female model. After that, while that human model is ready, then we can manipulate or we can provide the anthropometric dimension for various body parts. Based on that, we can create that human model. While that human model is created, then there are two options. One is basic scaling. So this is coming under basic scaling. Then we can go for body part scaling. Individual body parts it is possible for further scaling of individual body parts. So this is for overall body. Then we can go for only we can further, when that human model is ready, then we can go for further modification or further refinement of individual body parts. Say for example, for lower arm length we can modify the lower arm circumference. For that purpose we have to go for body part scaling. So in this way, software to software there is variation in terms of number of anthropometric variables considered for creating the digital human model. At the same time, various types of anthropometric database incorporated in that software, that is also different for different softwares. So in this way, using different types of digital human modeling software, here only we discussed about the example of CATIA and JAX, but we can use any other software like Ramsys, SAMI, Santos. With this type of software, we can create digital human model based on our anthropometric data. Further, again we can manipulate biomechanical data also. There is in all these digital human models, there is options for modifying the joint limit, means range of movement modification. There is provision for defining the comfort joint angle for different body joints. So based on that, we can also modify biomechanical data for that particular human model. So after discussing about how to create digital human model using anthropometric data, using different types of softwares, now we are going to discuss about how we can provide appropriate working posture while we are interfacing that human with the product or workstation model. So here is an example. So where we have digital human model as per our anthropometric data, after that we need to give proper posture, particular working posture, while that we are trying to simulate that digital human model is doing some activities in his or her respective workstation. Then first step is giving appropriate posture. That posture may be sitting posture, standing posture. Task to task it will vary. Now working posture. If we look at JAX software, in JAX software interface there are predefined postures. There is a lengthy list of postures, so that is already incorporated in that software. So when we are clicking on that right click on human model, it is showing postures, and there are so many types of postures. Then you can select whatever you require. Then it is easier for that user which particular posture you want to give to digital human model, so that you can interface digital human model with your product or workstation model. So this is from JAX software. From other software, say for CATIA software, in CATIA software there is also, after creating digital human model, you can manipulate individual body segments. range, you can change the motion of individual body segment based on this one. These are the segments list, and then you can change the degree of freedom here, that whether this is flexion, extension, abduction, adduction or rotation, and accordingly you can change the angle also. This is for different body segments. But there is also, like JAX software, here is the standard postures. Similarly, here are also few standard postures are defined: stand, sit, span, kneel. So this type of standard posture we can directly put on human model. So these types, from software to software, how to create posture, define posture, that is different. In some software there is already predefined postures, you can directly use those predefined posture. But for other software, what you can do, you can give some initial posture. After that, using body segments and joints, you can manipulate those body segment and joint, and accordingly you are providing a working posture to the digital human model. The same thing is also available in JAX software. So here is the example of if we are using CATIA software or Delmia human. In that case, how we are giving posture. So first we are selecting that posture, then from the posture we want to this tool is called posture editor. So posture select, we are selecting that mannequin, this particular mannequin. For that mannequin we are going for editing the posture. So this is a particular tool which we need to use in case of CATIA software. Then while you are clicking on the tool, then this type of window is opening where you can find different body segments. You can select, say here it is selected forearm. So forearm is selected. For forearm there are different degree of freedom, flexion, extension. So that type of, from this drop down menu you can select. Then you can change the angle. Accordingly it can be moved. Then the posture, predefined posture is initial. Initial standing posture is there. Again you can directly change it to sitting, sit, stand or kneel. This type of other posture also you can go. Then here is that example. So if we are modifying that particular body joint angle, then this type of different posture we can create using manipulation of position of different body segments by changing the angle of body joints. Similarly, in JAX software, how we can manipulate the posture. After giving the standard postures, then for fine adjustment as per the requirement of the task or for your simulation purpose, then you can go for this type of adjust joint. Then you can select that particular joint from here. Body part you can select that particular, here it is shoulder is selected, and under shoulder then you will find 3 degree of freedom, and in each degree of freedom you can change the angle, and accordingly you can manipulate the posture of that particular body segment. Moreover, in JAX software there is, apart from this type of standard posture which you can directly go for, even for individual segments like hand, you can give specific type of posture like grasp, grip, pointing. This type of posture, hand posture also you can directly provide to the digital human model. Otherwise, most of the software, what you have to do, individual body segments and its associated joint you have to manipulate as per your requirement to make your simulated working task. In JAX software there are other options also, like you can select this tool called human behavior. From human behavior you can select that particular human. You can select various body parts, like this is the trunk portion. After selecting the trunk portion, there are different types of hold orientation, release, keep vertical, this type of manipulation. After selecting this one, then you can, there are so many vertebral segments, but all the vertebral segments you can manipulate together with this type of human behavior tools. So it makes much more easier to provide a particular posture. Now, so after giving the initial posture to digital human, so first what we did, we created digital human models as per our requirement, that may be as per the anthropometric data. So we have example, we have created 50th percentile digital human model, 50th and 90th digital human model. Now as per our need, we are giving them sitting posture or standing posture, as we have already explained how we can give a particular posture. We can provide a working posture before interfacing that human model with the product or workstation model. So while we are positioning that human model with that appropriate posture, we need different types of reference points in how we are positioning the digital human model, or how we are interfacing the digital human model with respective workstation or products. For that purpose, we will discuss different types of reference point. So first reference point, so these reference points are important for positioning the digital human model in workstation. So first one is H point or hip joint point. Second, accelerator heel point. Third, seat reference point. Fourth, neutral seat reference point. Then there is sitting reference point, design eye point. We will discuss one by one. So first H point, if we discuss. So what is H point? H point means hip joint point. If we look at this anatomy of human body, then you will find there are two hip joints, left side and right side hip joints. From this hip joint, our femur bone actually moves around this joint. So this is a ball and socket joint, and around this there is 3 degrees of freedom. So these 2 points are known as, this point and this is the second point. These 2 points are known as hip joint point. This hip joint, if we connect with an imaginary line, this line does not exist, this is an imaginary line. The middle point of that imaginary line is known as hip joint point or H point. So based on that H point is very important for us, because while that is a sitting workstation, then how the digital human model is positioned on that seat, that positioning is depending on H point location. Now if you look at this one, so its position at the hip joint point, these are the hip joint, but hip joint point at that particular reference point at the middle of this line. So we can define what is, if we define the hip joint point, we can mention as H point or hip joint point is the midpoint of the imaginary center line which is connecting two hip joints. Now if you look at this particular image, while this is for automobile driver, where the driver is in seated posture, and then from side view we can find out that hip joint point is there. So this is the actually, here is the location of femur bone, and this is that hip joint with the pelvic girdle. So this particular joint, this particular point is called hip joint. Now this is from side view, but from front view or back view, the position of actually, as we mentioned, this is the midpoint of the body. So H point from side, back view or front view, it will come at the middle. So in sitting posture or workstation where the task requirement is the task requirement requiring seated posture, in the situation, first you have to give that appropriate sitting posture to the digital human model. After that, based on you have to position human model on the seat in relation to its H point. For automotive industry, while we are positioning or we are defining this H point, for that purpose H point machine or H point mannequin is available. So this is the 2D template where you can see H point device as per SEJ 826 standard. According to the standard, so this is actually representation of body form of 95th percentile driver. So this is the upper body, mean trunk portion, and this is the, you can mention as the thigh portion, and this is the lower leg. So this is the location of H point. This is the pelvic segment, lumbar segment, and thoracic segment. Now, while we are defining in automotive industry, there is requirement of defining the H point for the manufactured seat. While one seat is being manufactured, then we need to define the H point location based on this H point mannequin. So while we are positioning this H point mannequin or H point device on that seat, then seat is being compressed, and while seat is being compressed, then on the compressive seat, this H point machine is designed in such a way it represents the actual movement, body defined body segments, and as per its mass. So this is actually this H point machine or H point mannequin representing 195th percentile driver seated on the driving seat. And this is the, as per the instrument or device, this is the location of H point. So actual H point location is this is the one hip joint point, and that side another hip joint point. So finally the H point is locating here. So that H point location is important for automotive industry while they are manufacturing the seat. Not only H point machine, for position, for defining the H point, there is other tools also. For example, head rested measurement device on H point. So on H point mannequin or H point machine, we can also put head rested measurement. While one driver is seated on the driving seat, while he is using head rest, then where should be the optimal position of the head rest? That also we can study with this type of additional features. Now next we are discussing about seat reference point, SRP, neutral seat reference point, and SGRP, seating reference point. So first we are discussing about SRP. SRP or seat reference point. How we can define SRP? SRP for any seat, this is a point on the seat where the midline of the compressed seat back and midline of the compressed seat pan intersecting, this particular point. So intersecting point of midlines of compressed seat back and compressed seat pan is intersecting at a particular point. That point is known as seat reference point. So although it's positioned at the middle, but from the side view it will be visible at this side, from side view. Now next, neutral seat reference point. If we take the example of automotive industry or automobile design, automobile interior, so vehicle car seat moves forward and backward so that we can accommodate driver with shorter body dimension as well as driver with larger body dimension. So while driver is seated on the driving seat and he or she is adjusting the seat forward and backward, then neutral seat reference point is a location of the seat reference point which actually is preferred by 95th percentile driver. So 95th percentile driver, while he or she is seated on the, so in general while you are talking about in an analysis 5th percentile driver, then generally we consider pooled data, mean not male data or not particularly female data. So combined data, that is called pooled data. So 50th percentile pooled driver while seated on the driving seat and adjusting the, because he or she has to hold the steering wheel, has to operate the different types of pedals, accelerator, brake, clutch, while they are operating these types of controls, then they will adjust their seat forward and backward. So 50th percentile driver selected seat position, while 50th percentile driver is adjusting the seat as per his or her requirement, then the location of SRP on the seat, that is called neutral seat reference point. Similarly, this seat reference point, again while 95th percentile driver is adjusting the seat forward and backward, then 95th percentile driver selected seat reference point is called SGRP. So it will be more clear if we explain with diagram, with sketch. Now, so if we imagine this is the driver, this is the steering wheel, driver's leg is on the accelerator, feet is on the accelerator, and this is the steering wheel. If we consider this is 5th percentile driver, then this is the seat for 5th percentile driver and this is the SRP. Similarly, on the same seat, while 50th percentile driver is sitting, automatically their leg position should be the same, but they will move the seat a little bit backward, and if there is provision, they can move it a little bit upward also. So this location is, if this is 50th percentile driver, then this particular location will be NSRP, neutral seat reference point. Then if seat is moved further for accommodating (95th percentile driver), if this is the seat position, in this case, if we imagine this is 95th percentile driver and so this point will be SGRP. So while driver is adjusting the seat forward and backward as per the requirement, then all these are actually SRP. SRP means, as we discussed, that midpoint on the seat, which is representing the midline of the compressed seat bed and midline of the compressed seat bed. So that's location of SRP. As the seat is moving, it is also moving. So while 50th percentile driver is adjusting the seat, at that time the position of SRP is actually known as NSRP, neutral seat reference point. While it is adjusted by 95th percentile driver, while driver is adjusting the seat as per his or her requirement, Then 95th percentile driver selected seat reference point is known as SDRP. So these three reference points are important while we are positioning our mannequin on the automotive seat or any other seat where there is task requirement, seating task requirement is there. So after discussing about H point, the SRP, NSRP and SDRP, then we want to discuss another point, that is, here it is mentioned as AHP, accelerator heel point. What is accelerator heel point? Accelerator heel point is another reference point. Here we can show this one. If this is the accelerator, while drivers are keeping their leg on the accelerator, then their heel touching on the ground at a particular point, that point is known as AHP, accelerator heel point. So accelerator heel point can be defined as a point on the vehicle floor while driver are keeping their feet on the accelerator, then that particular point where the heel is touching, that contact point is known as accelerator heel point. This accelerator heel point is also important for positioning driver on the occupant seat. And this, while drivers are keeping, if we draw it in bigger, then if this is the leg and if this is the accelerator, then this point, as we mentioned, the point where heel is touching on the ground, so this is AHP, accelerator heel point, and the portion of the leg which is with this portion we press the accelerator. This portion is known as, so this portion is actually below that finger or phalanges bones. This portion is called ball of foot. So while drivers are keeping their leg on the accelerator, so here we need to mention that this accelerator is in undepressed condition. While drivers are keeping their feet on undepressed accelerator, then the point on the ground where the heel is touching, that point is known as accelerator heel point. Now, if we come to this image, then here you can see two driver, one is 95th percentile male, that is the representation of larger body dimension, and another is 5th percentile female, that is the representation of shorter or smaller body dimension. These two mannequin is positioned on this vehicle seat. So as per their requirement, they will move the seat forward and backward, and if there is provision of again up and down. So here you can see 95th percentile driver or 5th percentile driver, they are keeping their feet on the accelerator, and this location is accelerator heel point where heel is touching, accelerator heel point. And now you look at the posture. This is the typical driving posture, and this is the position of the seat. On that seat, this point is SRP, because this is the midline of compressed seat back and compressed seat pan. So from side view, this is the position of SRP. SRP for 95th percentile driver, because as per 95th percentile driver, this seat has been adjusted. So this is 95th percentile SRP, SRP for 95th percentile male driver. Similarly, female driver of 5th percentile female driver, while she is adjusting the seat as per her requirement. So seat will be moved little bit forward and little bit downward. So that's why SRP location has also been changed from this point to little bit forward and then downward. So this point, that seat reference point, it is 5th percentile driver selected SRP. And on both the mannequin, this is the location of H point for 95th percentile driver, and this is the H point to mean hip joint point for 5th percentile driver. Now you can understand, so what's the relation between SRP, seat reference point? Seat reference point is located on the seat defined, but its position may change as per the shifting position of the seat. As the seat is being moved forward or backward, so accordingly position of SRP is changing in 3D space, but in relation to seat, position of SRP is fixed in relation to seat, but in relation to space, SRP location is changing. On the other hand, if you look at H point, so H point for this particular individual, it is fixed, but individual to individual as per percentile variation or individual variation, H point location is also different. If you see from this seat surface, H point location is this much high, but here height is more. In SI, if we look at SI standard, although we mentioned that 95th percentile driver selected seat reference point is known as SGRP or sitting reference point, but in SI standard, this H point is actually mentioned as SGRP. So in SI standard, H point of 90, this is also used for positioning the digital human model or defining the position of mannequin on the seat. This H point location, H point of 95th percentile driver is referred as SGRP, sitting reference point in SI standards. But in general purpose, we can mention 95th this SRP is also mentioned as sitting reference point, SGRP, for normal purpose, where we are discussing about SRP location as per different percentile. So for 5th percentile there is no specific name, but for 50th percentile driver selected seat reference point is called neutral seat reference point, and 95th percentile driver selected seat reference point is known as SGRP. In SI standard, apart from that SRP, this H point of 95th percentile driver is mentioned as SGRP. So in SI standard, SGRP means H point location of 95th percentile driver, male driver. Now we are moving to the next important point, the reference point, that is known as design eye point. This design eye point is used in aerospace or aviation industry. In aerospace and aviation industry, in this case, if we look at automotive driving, in that case location of eye position is different, eye height is different. So they are viewing visibility outside the vehicle is also different, as the eye position is height as per the seat position is almost fixed, only moving forward backward, but if you look at the eye position, then their eye position is different. So their visibility outside the vehicle is also different in case of automotive vehicle. But in case of aviation aerospace industry, looking at the displays at the same time looking outside is very important. So for that purpose, all the pilots' eye position should be same. In this case, we need to adjust the seat. Seat can be moved up and down to accommodate smaller pilot and larger pilot, means pilot with smaller body dimension or pilot with larger dimension. All of their eye position or eye location should be at a particular point, particular location. This point is known as design eye point. So during manufacturing of that aircraft, this manufacturer has to define this design eye point. I mean, this position is fixed so that all the drivers' eye location will be nearby this value, so that all of them can see the important display. Here it is head-up display, so they can see the head-up display, at the same time they can see the outside, and they can also look at other displays. So for this purpose, all of their eye point is fixed, but their sitting location is different. So there, this is the, if we think this is the seat back and this is the seat pan, so seat will move upward and downward along the seat track travel, along the seat track, seat will travel up and down, so that it can accommodate pilot with smaller body dimension as well as pilot with larger body dimension. So what will happen here, this is the neutral seat reference point and here is the H point. So this is the H point of 5th percentile or smaller 2.5 percentile pilot. So for smaller pilot, this is the H point location, hip joint point. For large pilot with larger body dimension, their H point location is this one. But if we look at the NSRP, neutral seat reference point, obviously this is neutral seat reference point, mean midpoint of that seat track travel. Next, this seat can move upward if it is adjusted as per the 5th percentile driver, then this will be SRP, and if it moves down as per the requirement of 95th percentile or 97.5, mean larger pilot, then that will be, if it is adjusted as per 95th percentile, then we can mention that is another SRP. So SRP is moving from this point, this seat is moving up and down to position different percentile pilot, and accordingly we can identify the location of H point and location of the seat reference point. So main difference between the earlier discussed points, that is accelerator heel point and H points, here in automotive industry the main concern was sitting position is almost same, because there will only seat will move forward backward, so that they can operate different types of foot pedal controls and they can hold the steering wheel. At the same time they can see outside obviously, but their eye position is different. But in aviation aerospace industry, this design eye point is fixed, so that all of them has to see the displays, at the same time they have sufficient external view. For that purpose, seat will move up and down, so that it can accommodate pilots of different percentile. So after discussing about so first we discussed creating digital human model. After creating digital human model, we gave appropriate posture. After providing appropriate posture, then we position digital human model on the respective workstation based on defined reference points. So while we are positioning this digital human model or mannequin on that seat or any other workstation, then we have to think that as per that H point, as per that seat reference point, whether that model has been positioned correctly or not. So we can go for visual inspection as well as visual inspection for what? Visual inspection for whether that model has been oriented properly. If this is the seat, whether that pilot has been positioned at the middle of the seat for evaluation purpose. And this back, whether their spinal curvature or vertebral curvature is matching with the profile of the seat. You can see, so accordingly we have to position the human model based on the different types of reference point. Here accelerator heel point, H point, SRP. So based on all these reference points, we need to position correctly. We need to position that human model correctly on the seat. Similarly, in other workstation, if that is a industrial workstation where there is standing working posture, in standing working posture, that time also the orientation of human figure with respect to that product or workstation model, it should be appropriate. Then only we can go for evaluation, whether it's ergonomic or human factor evaluation. So now, while positioning that human model in that workstation, we can check that whether that positioning has been done properly or not. For that purpose, we can go for crash or collision detection. While you are positioning human model in front of this facility wash basin, so if any of this mannequin's body parts touching with that workstation model or workstation components, then we can identify that. So for here it is touching with this portion. So automatically, how will we position? So we can keep it little bit away, then gradually moving towards that product. If it touches with that product, then that touch can be identified with this clash and collision detection. For that purpose, in different software, JAX, AMI, AMSYS, Santos, in different types of software, they have defined this type of clash and collision detection tools. Here we are taking the example of CATIA software. In CATIA software, there is one tool called clash tool. So if we define that clash tool, if we click on this clash tool, then we can find this type of clash check. So here you can put the name, then type which type of clash you want to detect, then for which body parts you can mention. For only for the, you can select like this way. You want to select the we want to check the collision between any of the body segments of this human model with the product or workstation. Then it will show this type of clash, at which portion it is touching. So this is highlighted with red color. So in two places. So interference happen in two places, that two you can select one after another, then you can identify that where that clash is going on. And number, here the number has been provided, number of collision 2. So in two places that human model is colliding with the product or workstation. If you can find out where that collision is there, then accordingly you can shift the position of human model and model to simulate correctly. Otherwise, you will visually you have to inspect, you have to rotate that human model or product model to visually inspect whether any human body segments is colliding or interfering with product or workplace component. Now, contact clash. There are different types of clash. Selection against all. So selection against all, there are also selection type is also defined. Whether we want to detect the clash between this human model and another human model, between two human models body parts, or human model versus products part, or any particular body segment of human model with any particular segment of the product. So in different types of clash we can identify, and accordingly we can modify the position of that mannequin and then further go for evaluation. There is another tool for clash detection. There is also 3-4 options: clash on, clash off, and restrict movement. So in that case, so in just this is an example. In this example, while this hand is touching with this portion of the wash basin, then what is happening? It is highlighted with red color circles. Then you can easily identify that this particular body segment is actually interfering with this particular segment of the product. And there is this type of option, that while you are moving that human model from this side to this side for positioning it properly, if it collides with that product, then it will restrict the movement. So this type of tool is also there. So further you cannot move forward, because while if you keep it on, then while you are moving that human model towards the product or facility, then whenever there is a collision, it will stop the movement. It means that is the final position, it cannot go beyond that. Then there will be some interference. So in this way, in defined software, there are defined. So this is example from CATIA software, but there are other softwares. In all of the softwares, this type of facilities are available. With this facility, this type of tools or menus, we can easily identify that what type of class is happening, and accordingly we can simulate our work environment. So far what we discussed: creation of digital human model, then providing different types of posture, understanding different types of reference point, and positioning the human models or mannequin, or interfacing digital human model or mannequin with appropriate posture, following different types of reference point on their respective workstations. Now, as this course, many of the students are from India who enrolled for this course, Digital Human Modeling and Simulation for Virtual Ergonomic Evaluation. So, I think many students will be interested to know what's the present status of digital human modeling teaching, research in related to education and research, how in India this research and teaching is going on. So, for that purpose, I am referring one paper published by me in 2014. So, after 2014, if we see, there are 18 publications related to application of various types of digital human modeling software for various types of product or workstation design and evaluation reported from India. Similarly, related to research and development, mean either creating digital human model or modifying its body parts, that type of research, reported research is 8 in number from India. Similarly, literature review based paper or review article published from India till 2014 numbers is 6. So mainly in India, if we see the publication, so main publication is related to application of digital human modeling software for various product and workstation design. But R&D activities are very limited, and also few review based articles are also available. So from this module 4, what we learned? If you recapitulate from very beginning, then we will find in module 4 we have learnt about physical digital human model versus cognitive digital human model, their definition and what are the difference between these two. Then evolution of digital human model, how digital human model evolved years after years starting from 1960s to till date. Then history of various digital human modeling software. We discussed about Bowman, Combiman, CrewChief, and gradually moved to SAMI, Ramsys, and latest software like Santos. Then we also discussed about interfacing CAD product or facility with digital human model. We discussed about how to create digital human model as per anthropometric data, how we can edit anthropometric data for the digital human models. Then providing appropriate working posture to digital human model, various types of reference points, clash and collision detection, and current status of digital human modeling, teaching and research in Indian scenario. Now I will suggest all of you to download this paper and go through, then you will get clear picture of Indian scenario, digital human modeling and simulation in product and workstation design, Indian scenario. So in India, what research is going on, which are the institutes or organizations doing research and teaching related to digital human modeling. So here all those informations are there, you can go through. I just want to highlight few areas like so if you look at this particular section, research and development initiative. So all the references are there, you can go through, you can explore these references, then you will get more information related to research and development initiative related to digital human modeling which are going on in India. So these are some picture from those published papers where movement of eyeball, then view field related research is going on. Then application oriented. So if we go through all these references, then you will find there is digital human model has been used for posture analysis, design and spatial layout of playing equipment, ingress egress analysis, anthropometric size measurement of Indian driving population, modeling for anthropometry, vision analysis of jet aircraft pilot. So various types of application of digital human modeling, various different digital human modeling software has been done in Indian scenario. Similarly, review based publication, if you look at, so these are some information related to review based paper. So I suggest all of you to go through these differences, then you will find more information related to use of digital human model in India. Then if you look at this side, there is a list. These are the academic or research institutions in India which are using digital human modeling software for their research or product or any other facility design purpose. So Center for Design and Management CPDM, IISc Bangalore, Design Department IIT Guwahati, Department of Human Engineering and Human Factor, Indian Airports. So many other institutions are there who are using digital human modeling software for their research and development purposes. These are mainly academic institutions or research institutions. Other research and development organizations like Defence Institute of Physiology and Alliance Sciences, Delhi, Automotive Research Association of India, Pune, Hindustan Aeronautics Limited, Bangalore, Aeronautical Development Agency, Bangalore. So these are various R&D organizations which are using digital human modeling software for their product and facility evaluation. Then various industries. Here are few industries names are also mentioned. So from the literature, it is found that in these industries also digital human modeling software has been used for their either their manufacturing shop floor or various types of product evaluation. These industries are using digital human modeling software. So from this paper, we are getting detailed information related to use of digital human modeling software for research purpose or teaching purpose in India, and number of paper published in various fields. Like this one, review paper, R&D related, research and development related papers, and application related papers. Now, various online useful resources. These are the softwares available in the market, and these are the links of those softwares web page. If you explore these websites, then you will find more information related to individual software, their capabilities, their limitations, as well as when they are developed, how they are moving forward for making the model more refined. So all this information you will be able to see. Now these are the list of references which have been used for in various slides. And also I would like to suggest you to download these papers and go through, then you will get more clear idea about application of digital human model, creation of digital human model. This is the list. So thank you.